Now that we managed to trace over the environment, we can look at this expression from a purely mathematical point of view. So think about this expression as a map that takes operators acting on d-dimensional Hilbert space into operators acting on d-dimensional Hilbert space. We will consider the situation where the dimensions are different later on. But for now, assume, you can just even think about in terms of matrices. So assume that your row is d by d matrix, and the result of this map is another d by d matrix. Now, looking at this map, what can we say about the properties, mathematical properties of this map? So one thing that you can see right away is that it is a trace-preserving map if you impose extra condition on the Kraus operator. So if you take the trace of this expression here, you can see that we can make a cyclic permutation under the trace, right? So the trace is invariant under cyclic permutation of operators. And so if we take the trace of this expression here, then I can do the cyclic permutation here. So I can put this operator here, and I have this expression here. So you can see that as long as we assume that this is equal to the identity, which is the condition that we impose on the Kraus operator, so as long as we require that the sum over k ek dagger ek is equal to the identity, so it's d by d identity matrix, so then this map is trace preserving. So that's this condition gives you the trace preserving property for this map. Now, this map also preserves positivity. So if your operator row is positive, then again, if you look at this expression here, then you can see that the positive row can be written as a square. So you can take the square root of row, right? Because it's a positive operator. So therefore, you can write this expression here as ek square root of row ek dagger, but then you can see that this in fact is a product of a matrix with the Hermitian conjugate of the same matrix. So this is a positive matrix, so therefore the sum of those positive matrices is also positive. So then it's clearly this map takes positive operators, positive matrices into positive semi-definite and non-negative matrices into non-negative matrices. So we say that this map is trace preserving, and this condition here, we also say that it is positive or positivity preserving, but we just simply say it's a positive. So it's a positive trace preserving map. Now, the final question is, given this map, it's a well-defined map. Once we specify the Kraus operators, and if we request this, so we have a well-defined positive trace-preserving map. Then the question is, can we choose any other set of the Kraus operator? So the answer is yes, actually we can. Remember, when we derive this particular form from the unitary evolution of the whole thing, the system plus the environment, at this point you could be rightly concerned, because you can say, well, the Kraus operator is associated with the corresponding state of the environment, the basis state, and the environment could be huge. So this expression can have just like a zillion and zillion of terms, and that's kind of weird, because each operator, each Kraus operator, is d by d matrix. So so obviously it can be expressed in terms of basis in the space of d by d matrices. So we know that the space of operators, or the space of, say, d by d matrices, form a vector space on its own. It can even be a Hilbert space, because you can choose a set of operators bi that serve as the basis, and you can then define the Hilbert-Schmidt inner product, as you remember. So you take trace bi dagger bj, and that is your inner product in this Hilbert space. So you can choose a set of orthonormal or mutually orthogonal vectors, which are in fact operators, the basis operators, and then you can decompose those Schmidt operators. Sorry, you can decompose those Kraus operators here using the Hilbert-Schmidt basis. Now, this is a d-squared dimensional Hilbert space. So when you take a look at this expression here, and you pick up your basis operators, so bi here, then every single Kraus operator here can be expressed as a linear combination, of course, of vectors of basis operators. So that you can do. So you can substitute for EK a linear combination of basis operators, and of course, you can take Hermitian conjugate and do the same for this EK dagger. So once you do that, you can see that you have some sort of expressions in front of so you have a linear combination of terms which are almost right but not quite, because you have those cross terms. All right, you have operator from one of the basis operator bi, and there's a bj dagger. So you would like to have the same index here, but that's kind of easy to see that you can reduce it to the expression where you have the identical index, simply because if you look at this product here and treat it as a matrix, you can see that it's just a positive matrix that has a spectral decomposition. So you can write it as a product of the unitary matrix, the eigenvalue that is positive, times the Hermitian conjugate unitary matrix. So when you do this using the spectral decomposition, you can rewrite this expression here in terms of the sum over Pm. Pm is the eigenvalue of this matrix, the positive number. In fact, you can show that all those numbers add up to 1. So sum over m Pm is equal to 1, and m goes from 1 now to d squared, and those operators here are the unitarily related to the original basis vector, so that you picked up. In fact, you can show that as long as this matrix here is unitary, the operators A form also the orthonormal basis with respect to the Hilbert-Schmidt product. And and of course, if you really so this is already a very nice and compact expression, right? So this index goes through all values of m from 1 to d squared. But if you really want to write it as in terms of in this particular form, so then you can just simply write this as a sum over m, and when you put it a bar m rho a m dagger bar, where a bar m is square root of pm a m. So you can put a square root of pm here and incorporate this into the definition of a. So the bottom line here, so to speak, is well, let's make it a bottom line here, is that we need at most d squared Kraus operators. So there's no need to worry now. You can see that the same map can be expressed in a rather compact way. You don't need more than d squared Kraus operators. If you are dealing with a system of dimension d, at most you need this d-squared Kraus operator. So in summary, we do have positive trace preserving map. The trace preservation condition is due to this extra condition that we have here, and so we can see that this map maps positive operators into positive operators. It preserves traces, and also it can be expressed in all kinds of different ways. So the Kraus representation of this map is not unique, but we can always write it in a compact way. We don't need more than d-squared Kraus operators when we deal with d-dimensional system.